My name's Tom Wheeler. I'm a principal curriculum developer at Temporal, previously as principal curriculum developer at Cloudera, developed training courses there. Prior to that, I spent half my career as a software engineer. In either of these two roles, though, I have spent basically my entire career working with all sorts of systems. A lot of that has involved distributed systems, either designing them, developing them, or teaching people how to use them. And so that's the nature of my talk this morning. I want to time travel a little bit. Let's go back to, let's say, 2009 or any time before then. The way that we developed software back then, you'd write an application. It ran on typically a single computer, maybe a small number of computers. Those were located in a data center inside your location. So you were limited to the number of machines that would fit into the rack that you could convince your boss to buy. There were a lot of limitations in the hardware that was available. The consequence of that for your users was poor performance because the application didn't scale to where it needed to be. Things tended to be very slow because you were limited by the hardware that was available. Also, because everything was running in a local data center and you were limited by the hardware that was available inside of there, you had limited availability because you might have everything in your application certainly running in a single data center or running perhaps in a single rack within the data center, perhaps even running on a single computer in that rack in the data center. And if any one of those things goes down, your application goes down with it. There were also consequences for developers of this situation. We had limited velocity because we were developing monolithic applications. Everything was all in one place. And the possibility of breaking something in one part of the application came about as you were developing a completely different part of the application. If you made a change to the database schema, for example, that had to do with how user information was stored, that could wind up breaking something in a completely different part of the application. The result of that was long testing cycles. And then when you got to the point of integration, different teams that had been working on different parts of the application by themselves, when they came to put everything together, they found out that things were broken. So you had to do a lot more testing. You had to call off at the last minute some updates that you were trying to make. So the cost of the development of making any change to your application became very high because of these integration problems. Also, tying back to the everything running on physical systems that were available that you had, there was limited efficiency because I don't know, some of you were probably developing software back then. Some of you may be young enough to the industry that you don't recall this, but the way it was, because I went through this myself many times, I'd have to convince my boss, okay, we need some number of servers. And then we would negotiate about the specifications and figure out what size servers we need. Then we'd have to talk to somebody in accounting. We'd have to fill out forms, place an order with a vendor like Dell or Compaq or HP. We'd have to wait for those servers to get built and shipped to us. The system administrators would have to configure them, provision them, physically plug them into a rack, plug the network cable in, and only then did you actually start deploying your software to them and using them. So it was a very slow process. You couldn't respond to scalability problems on demand. Like if you had a scalability problem, it was too late because it took 3 months to get another server. You had to buy more server than you needed right now because you knew that 3 months the application was going to grow and you wanted to have the headroom to expand to meet that demand. So that was the situation in 2009. I want to talk about a couple of trends that have improved these situations. The first is that we've begun moving our infrastructure to the cloud. So you no longer have to provision physical hardware in many cases. You can provision a virtual machine or perhaps a Kubernetes cluster. And you can do that in a matter of minutes. And probably you don't have long requisition cycles like you had before. Maybe in some companies, you have to still convince somebody about the expense that you can have. And they'll complain when you forget to shut something down and rack up a larger bill than you expected. But the point is, it's very easy compared to 2009, very easy now to deploy the infrastructure that you need to run your application. Also, the availability situation has improved because you can provision not only a new server, but you can provision servers in different availability zones within a region. And in fact, you can provision servers in different regions entirely. So you can put the application closer to the users who are using them. That improves performance. So that's a net benefit that we've had here moving to the cloud. Another improvement that we've made is in the design of the applications. Rather than having everything as a monolith, everything running inside the same application, we've broken apart different services and we've put them into their own instances. So the application, instead of making a function call within the application, it makes a service call to something run across the network. And so each of those services can be scaled independently. They can be deployed and upgraded independently. The service can be implemented in a different language, in a different operating system, running potentially on a different platform. It doesn't really matter to the caller how that thing is implemented. It's a black box. But the application teams that develop and maintain those services, they're free to make whatever changes they want. They can use any database they want. They can upgrade it whenever they need to, so long as they don't break the contract provided by the API. Everything just works. And so what would have previously been a function call is now a series of remote procedure calls when you're calling service A, and then perhaps based on the result you get from that, you call service B, and then later you call service C. So for your application to work, all those services have to be up and running. And so that's created a bit of a problem because modern applications, because of the trends that I've described here, modern applications are distributed systems. Instead of function calls, you have remote procedure calls. Back in the 1990s, Sun Microsystems, some of you may remember them, great company. They had the slogan, "The network is the computer." They were a very network-centric company. They built workstations and servers and really powered a lot of the early internet. Some of the engineers there came up with what they called the fallacies of distributed computing. It was a series of 8 rules that were basically what young engineers believe about networks, and then later find out that these things are not true, usually because something failed. So you go out to build an application and you design it thinking the network's reliable, or that the latency is 0, or that there's an infinite amount of bandwidth. And the reality is that these things aren't true. So these 8 rules still are surprisingly relevant even today, but I can save you a lot of time. You don't have to learn all 8 rules. The rule that matters, the lesson you should walk away from, is that when you add more networking to your applications, it comes with more opportunities for failure. If you're making a function call, for example, you know that the other side's going to be there because it's inside the same process, and you're just communicating within memory within the same process. When you add a network to this situation, then it could be that the service you're trying to call is down for maintenance. It could be that their internet connection is gone. It could be that your internet connection is gone. There's lots of reasons why trying to call a service would result in something that didn't work. So here's an example that I'll use to illustrate this. So here's a money transfer application. The idea is that we've got business logic that we connect to a banking service. We're going to do a withdrawal of some amount of money from one account, and we're going to deposit that same amount of money into a separate account. So think of some sort of money transfer application like Stripe and Square, perhaps PayPal or other applications of that nature. So it's 4 lines of code. I happen to write this in Go. The language doesn't really matter. Even if you've never written Go before, it's a simple enough example that I think you'd probably grasp what it's doing even without an explanation. But we create an instance of the banking service. It's a client. We call the withdraw function, give it a source account number, an amount that we call deposit with the target account number, same amount. And then we generate a success message based on the 2 transaction IDs that we got, that we return, this thing is successful. It seems so simple, right? It's 4 lines of code. How hard could it be? Well, let's look at how hard it could be. The first problem that you come across, as I mentioned, the service could be down or the network connection is down. So you can't make a connection for that reason. So you think, and I've been through this, probably many of you have written code like this yourself. I've done it in many applications over the years before I was aware of Temporal. But the solution then is instead of just making a call to the service, you move that call inside a loop. So you'd say for I equals 1 to 100, however many max attempts you're going to have, and then you make the call. And if it fails, next time through the loop, it's going to try again. Eventually, it's going to succeed, or you will have used up your maximum number of attempts. Easy enough. Okay, we added a few lines of code by putting it into the loop. Well, the problem is, and I experienced this myself, because I did exactly that when I was a young engineer, the service that I was calling was overloading. It wasn't responding because it couldn't handle all the requests that it already had. So I was making a bad situation worse by adding a bunch of additional calls. So I got an angry call from the system administrator of that service who said, stop calling this service. I said, okay, here's what I'll do. I'll add a delay inside that loop. So I'll make the call. If it fails, I'll delay 1 second, and the next time 2 seconds, the next time 4 seconds, and so on. So it takes care of intermittent failures very quickly, and then longer term failures, I'm not overloading the service. So, okay, easy enough, add a few lines of code. So here's what it looks like after you do that. That 4 lines of code that I showed you before, after you implement your own support for retries, here's what we have. It's not important to understand the code, by the way. I'm not here to teach you the Go code, but I just want you to see the relative increase. Before we had 4 lines of code, Now we have perhaps 15 or 18 lines of code. So then we get on to the next problem. And the next problem could be that we're calling the service, but the service returns an error. For example, you're trying to deposit money into an account, but that account is closed. So you can't put the money in there. So now the account balances are wrong because you've withdrawn money from one account. You can't put it into the other account. So you have to compensate this by putting that money back into the first account, effectively undoing that transaction. This is known as the saga pattern because you can't rely on a database transaction because potentially you have multiple databases. So that's the solution for that. And when we implement that, the code gets bigger. So we've moved from maybe 4 lines of code to 18 lines of code. Here we have perhaps 30 lines of code. And then we move on to the next problem. Well, the next problem is that we call the service, but it's slow to respond, perhaps because it's overloaded. So instead of getting a response back, it just waits and waits and waits. And now our application is hung because it doesn't move on to the next step. It's still waiting for a response. So the solution to that is to implement support for timeouts so that you say, we'll wait a maximum of 60 seconds, for example, for the response to come back. And if we don't get it, then we'll consider that request failed and we'll issue a new request or we'll print out an error message or whatever. So you add support for timeouts, and then this is what the code looks like. So looking at the before and after, when we went from 4 lines of code, that's the happy path, right? And then on the right side, we have a little more than 70 lines of code. And so that's the reality. And you'd think, okay, well, this is fine, but the application is reliable now. Is it reliable? No, it's not reliable. There's a lot of things that we haven't handled, but one of the most important things we haven't handled has to do with application state. So if we think about this, the correctness of this money transfer requires us to do the withdrawal and the deposit, and both of those things have to happen exactly once. So if we're running this thing and the process terminates for whatever reason, I'll illustrate some reasons in a moment, but let's say the program fails prematurely before we do the deposit, if we restart, then it will do the withdrawal again because we've lost all the state. And so it doesn't know where the thing is. If we restart it, it does the steps that have already been done before. So correctness requires exactly once execution. That's the root of the problem. So let's think philosophically about execution for a moment. The code that you saw before is static. The code doesn't do anything by itself. It's like a noun without a verb. There's no action there. It's like sheet music without an orchestra to perform it. To make any progress, you have to combine that code with execution. It's at that point that the operating system allocates the memory, the processor, whatever resources are needed to establish a process and to run that execution within that process so that it can reach the end goal. We're never going to reach the end goal if we don't have the execution. So we have a bit of a paradox. Execution is what brings the code to life, but it's also what introduces the possibility of failure. The code that you saw before, it could never fail if you never execute it. It's like the most secure computer, for example, is the one that you never plug in and turn on. It's that kind of situation. So what could go wrong? Well, the execution could terminate prematurely for all sorts of reasons. For example, you could have a bug in your code. If you're writing the code in C++, for example, maybe you have a memory error and then the program crashes for that reason. It could be that the operating system that your code is running on, Linux or Windows or Mac or whatever, it could be that there's a bug in that operating system. Windows, you get the blue screen of death or something like that, and then it crashes right in the middle. It could be that the computer reboots because the administrator has applied a software update that requires a kernel patch, the machine gets rebooted. It could be that the computer shuts down because there's a power outage. It could be that the computer hardware fails. Maybe the processor overheats and the computer just shuts down. And so maybe that is not an everyday occurrence, but if you're running millions of executions a day in a high volume situation, it happens all the time that you experience these sorts of problems. You have to be able to deal with them. The problem that we have, though, is that an execution is volatile. It's tied very closely to an operating system process. So if the process in that operating system terminates prematurely before the code reaches its goal at the very end, then the execution terminates. And all of the state, all the progress, all the variables that you've set, all the threads you've created, all of that information just disappeared in a flash. And it's gone forever unless you, as a developer, have taken steps to put that code into a database or into a message queue or something to sort of save it externally from the program. So what can you do at that point? Well, you could restart the program, but as I explained before, the correctness of that money transfer requires exactly once execution, and you don't want to do the withdrawal twice and the deposit once. That's not improving the situation. But if you've lost all the state, restarting is your only means of recovery unless you've built something for yourself. Well, the ideal thing to do, though, is somehow to resume the execution from the point of failure and then continue on from there as if nothing ever happened. What we want to do is abstract away the volatile nature of the execution. So that brings me to Temporal. Temporal is a software platform that provides durable execution for your application. It ensures that your application runs to completion, that you get this effectively once execution that I was talking about. It does this by automatically maintaining the state of your application external to the application. And then if the process terminates, it doesn't make it to the end, then it automatically reconstructs the state from before the failure and continues on from there as if the failure never happened. Additionally, it provides built-in support for managing retries and timeouts. So the code that I showed you before, how it ballooned from 4 lines of code to 18 lines of code to 30 lines of code to 70 lines of code, you don't have to do that yourself. You just write the code that looks like what it was in the beginning, the happy path, and you let the platform take care of retries and timeouts and things like that. That improves your productivity as a developer because you have less code to write, less code to maintain. The code that you write is easier for other developers on your team to understand, and it's easier to support. It's easy to reason about when something goes wrong, if you need to debug something. So that's what Temporal is. Temporal is also open source. It's released under the server. There's 2 components, a server-side component that tracks the application state and a client-side library I'll talk about in a moment. It's called the Temporal SDK. And both of those things are open source. The server-side software and most of the SDKs that we offer released under the MIT license, the Java SDK and perhaps 2 others are released under the ASL, Apache Software License. In both cases, very liberal, permissive licenses that don't require you, for example, to contribute your changes back and anything like that. But the thing that the license does require of you is that you include the attribution. So you can't, for example, take the Temporal source code and change it and then claim that you wrote the whole thing. You have to leave in the copyright notice. So if you look at the copyright notice for the server software, on line 3, we have Temporal Technologies. That's the company I work for. That's the company that sponsors the development of Temporal. And then you look a couple lines down and it says Uber Technologies, the ride-sharing company. And you think, well, that's odd. Why would that be? Well, let me explain why that would be in that. Temporal was started in 2019, but it actually traces its history back several years. In 2015, we had 2 engineers, Maxime Khativ and Samer Abbas. They were engineers working at Uber. They're the founders of Temporal, but they were working at Uber. Uber had moved from a monolithic application to microservices, and so they have these problems of orchestration like I was talking about before. So they built a system to try to improve that situation. They did it so well that all the other engineers within Uber saw it, and they're like, we have the same problem, and we want the same solution. So the implementation, which was called Cadence, that took off within Uber. It became very popular. But actually, this idea that they had for how to implement it goes back even many years before that. In 2009, Maxime was the tech lead at Amazon for the Simple Workflow service. Some of you may have heard of that. And Samer was working on the team with Maxime. So these 2 people who went on to become co-founders of Temporal, they've actually been working on this idea of durable execution for more than 15 years. And so this, even though it's the company Temporal and the software platform is less than 5 years old, the idea has been around, tested at production scale in some very large companies for a very long period of time. So if you think about the implementation of it, every Snap story, if you're familiar with Snap, the social media platform, every Snap story runs through Temporal. Every Coinbase transaction runs through Temporal. Every message on Twilio runs through Temporal. So it's already being used at production scale in very large applications. And people are comfortable using this technology because it's quite mature and has been around for some time. The core of Temporal development is called a workflow. And if you think of the word workflow, you probably have some idea of like a business process modeling tool, a low-code, no-code environment where you try to draw pictures of your application logic. That sort of thing usually results in frustration because it's difficult to express in those kind of systems what it is that you want to do. If you're a developer, you just want to write code. And that's what temporals are. Temporal has a workflows as code approach. A workflow is nothing more than a function or a method, depending on the language that you're using. Java would be a method, Go would be a function. It specifies the application's main business logic. In the case of the money transfer, that money transfer function would be the workflow. It benefits from durable execution that's provided by the Temporal platform. So if the termination or if the execution of that workflow terminates in the middle, it will be reconstituted automatically in a new process, potentially on a new machine in the case of hardware failure, and then continue on as if nothing ever happened. Because the workflows maintain state automatically and they're resilient to failure, they're capable of running for long periods of time. So as a developer, you may have never realized it before, but a lot of the design that you do is trying to keep the execution times of your application very short because you can't count on them running for very long. And so Temporal allows improvement in this way. As I mentioned, workflows are code. You'll write the code using what is called a Temporal SDK. It's simply a library that you add to your application, and you make a few calls, and you get all the benefits of durable execution. Temporal offers SDKs in 6 languages: Go, TypeScript, Java, PHP, and then .NET, which translates to C#. It could also be F# or other .NET languages as well. The functions that you do, or if you need to do failure-prone activities, such as querying a database or writing to a file or calling a network service, you would call that in a separate function. Separate from the workflow, you would put it in a function called an activity. It's simply another function, but because it is in a separate function, Temporal is able to monitor this call, know whether it's successful, and know whether it needs to be retried. So you get that automatic retry behavior. A function is referenced in your workflow, and as the workflow executes, it calls whatever functions are in there. You get that retry policy at the bottom, so you can control declaratively when the retries happen, the delay between them, how many maximum attempts you want to have. You can set timeouts. You don't have to write the code. You just set the policy that you want. So I mentioned that there's a service, and there's also a client-side library. The Temporal service, which you could run on the laptop for development, you could run in the data center, you could run it in the cloud, or you could use the Temporal cloud service that we offer, that manages and tracks tasks related to the execution of your workflow and activity code. It maintains and durably persists that information to a database for each execution so that if the execution terminates, it's available to be able to reconstruct the state. But the Temporal service does not run your code. It's merely tracking details related to the execution. There's another component called the worker, which is a part of that SDK that's provided that you put in your application. That is what runs your code. It runs your workflow and activity codes. Behind the scenes, that communicates with the Temporal server, and it pulls a task you maintain on the Temporal server that says what to execute. And it picks up the task, it executes the code, and it sends the result back to the Temporal service. That's how it's able to maintain this history of events that enables it to recover in the case of failure. So there's one platform, Temporal. You can either self-host the service, you can run it yourself, and you can run it on as many machines as you want. It's open source. There's no limitations on the size or commercial nature of what you're running. A lot of developers don't want to be system administrators. They don't want to get paged at 2 in the morning when the disk fills up with log files or something like that. So they want to use a cloud service so they can focus on development. So we offer Temporal Cloud, which is an alternative to self-hosting, fully managed cloud service with SLAs, support, and it frees you from having to secure and upgrade and monitor and maintain that. You let the experts at Temporal do it. But the choice is yours. You can either self-host it or you can run Temporal Cloud. So in conclusion, Temporal is an open source platform that provides durable execution. It ensures that your application always runs to completion despite any adverse conditions that would otherwise terminate that execution. Temporal applications use a language-specific library known as the Temporal SDK, available for the 6 languages that I mentioned before. Workflows are the fundamental building block in Temporal. It's simply a function that defines the business logic that you want to carry out. It's stateful, it's resilient to failure, and it can run for long periods of time. If you need to perform failure-prone things like calling a service or writing to a file, anything that has a possibility of failure, you would put that logic into an activity. It's simply another function that gets called within your workflow. If the activity execution does fail, it's retried automatically until it succeeds according to a policy that you can customize. The Temporal service works by managing tasks related to the execution and storing event history for every execution. It uses that, the worker uses that information to automatically restore the state and resume from a failed execution as if that failure never happened in the first place. And as I mentioned, you can self-host or you can use Temporal Cloud. So I recommend stopping by the Temporal booth. We have an exhibit in the main hall where you can learn more. We also have 2 prizes that you can sign up for. There's a Lego Dunes Royal Ornithopter, and then there's a Lego Darth Vader helmet. They're due to be delivered today. Hopefully they get delivered today. They'll certainly be here by the end of the week. So you can't see them in person yet, but we'll have a raffle for later in the week where you can put your name in and potentially win one of these prizes. And whether you come to the booth or not, I'd recommend going to temporal.io. That's our website. From there, you can find a link to our GitHub repositories. You can find downloads. You can find documentation, free hands-on training that'll teach you how to use Temporal. You can try it out for yourself, find out about upcoming events, and a lot more. So thank you very much for your time and attention. I appreciate it.